So in this tutorial, we are going to create our face recognition software. So we are going to create an avatar that is going to be able to look at the video and determine what face expression the person is having. You will be able to do this over your webcam or maybe load an already existing file. This is an extremely exciting project, and we will do this one in a bit different way than we have done our other projects. So if this sounds interesting to you, let's get started. So how is our development road going to look like? First of all, we are going to go through the theory and preparation. We are going to give a little bit of insight what deep neural networks are, what libraries we are going to use, how we are going to prepare the environment where you can download your dataset, and so on and so forth to prepare for the actual development. Then we are going to create and train our model. You will go through how to develop the theory that we have just mentioned into our model, how we're going to train it, what parameters we need, how we're going to create those layers. We are also going to explain what convolutional networks are, what deep neural networks are for, and how they can be used for image recognition. Then we are going to create the GUI. We are going to create a Python GUI using tkinter. We are going, as you have already seen, to live stream the video and our predictions, and also our avatar to our application. So if you're interested, let's get into coding. Okay, let's get started. This project is going to be a bit more complex than the other ones, since it's going to involve a lot of machine learning and deep neural networks. So I'm going to try to explain it from a light overview, so you can understand the code, what's going on, so that you could build something like this on your own. But I'm not going to go too deep into the mathematics and the theory behind it, since this is extremely complex and explaining all those little things behind it would take much longer than the entire course here. So, but you will be able to understand all those concepts and apply them into real life projects. Okay, let's get started. So I have a blank project open here. So like always, let us create a source folder first. And in this folder, we are going to have our application, and we are going to have our training data and our training Python file. So let's do those. So let's create a train.py, and let's create a emoji.py file, and let's create a data folder in which we are going to store all our data. But before we start, let us explain what we are actually creating and what components we need for it. Here I have my drawing board open, and as I have already mentioned, we are going to create a neural network. Why? Because neural networks are great for this purpose, for image classification, patterns classification, and generally classifying objects and extracting certain features out of them. So let us explain what is a deep neural network. A deep neural network is a normal neural network that has a certain level of complexity. So this means that it has more than 2 layers. So what do I mean by that? So let us examine this here. We have some information, some data that goes into our network. So this is the entry point. Then, so this is our entry layer, so to say. Then we have a hidden layer inside of that consists of a certain number of neurons that we are going to define later. And now we have connections all over here and all over here and all over here. So I didn't draw this too nice, but as you can see, everything is connected with everything. This is one layer. If we have more than one, so let's say we have 2 here, which are again all interconnected, like that. Then we have two hidden layers, which would make it a deep neural network. And then we have some output, which is this here, which will output our results. So data goes in here. We have a hidden layer that trains itself, that based on the inputs and the restrictions and the rules we give it, figures out some type of mapping and outputs data here. So a neural network in general is a technology that is built to simulate the activity of the human brain. As you can hear, we have neurons, we have connections. It kind of reminds how the human brain works. So why is this technique extremely good for finding patterns, recognizing data, and finding certain features in our input data? Because we can find features, certain features in our input data. So let's say we have an image and we want to classify only images that contain kids, for example. And this is a feature. So we could, while training the data, every kid has a certain feature. So a kid is smaller than an adult, it probably has a certain type of hair, certain size of shoes, and so on. And all those little features are great for specifying or for categorizing our input data. So the alternative to this would be to write those algorithms manually and really search, for example, the height of the person and specify, okay, if the height is lower, then the probability that it's a kid is like that. And if it has a t-shirt where Mickey Mouse is on the t-shirt, then the probability again increases, and so on. And we would need to create all those rules manually. And that's where neural networks are great, because while training our data set, we are going to create those feature hierarchies or feature layers that are great at examining and finding those specific things onto our dataset and classifying them. So what do those layers actually do? Each layer performs specific types of sorting and ordering in a process that can be referred to as feature hierarchy. One of the key uses of these neural networks is dealing with unlabeled or unstructured data because of that. So this is just a simple overview of how this works, and you will see all those layers that we have just mentioned here, how we actually implement them in code. There are certain mathematical operations that go into this, and this is where it actually becomes really hard. So each of those layers, as we have mentioned, is going to do something. It's going to sort our data, it's going to extract some values based on some mathematical formulas, and that's where the entire complexity of it gets to, creating those formulas, creating those models, and thinking of ways how to process the data. So this is where the hard thing is. But implementing that, if you already know what we want to do, is really quite easy, and you will see this right now. So let's return to our code here. We have a little bit explained what a neural network is. So in this case, we are going to create a deep convolutional neural network. So there is one more thing to explain here, what convolution actually means. It is a mathematical operation on two functions that produces a third function. So this is what we have already mentioned. So we get some shape that goes in, two values are somehow multiplied, some operation is used on them, and the third value is produced. I'm pretty sure most of you are familiar or heard the term TensorFlow, which is a library in Python that provides a lot of features to work with those machine learning algorithms. So we can even make this easier by using Keras, which is a high-level interface on top of TensorFlow that makes deep learning much easier, since it's going to provide us all that functionality through some functions and simple APIs, which we can always search in the documentation, and it's just going to make our life a lot easier. So let's start. The first thing we need to do is import a few packages. I'm going to paste those packages right here. Throughout this project, I'm going to copy and paste more code, since it's much easier if I paste the block here and then I explain line by line what it is doing instead of typing it out, since a lot of those operations can become quite complex and they're quite standardized and can be always referred to in the documentation. So here we have our layers. There are, for example, a dense, dropout, flatten layer. There is a convolutional 2D layer. Then there is Adam, an optimizer. Then there is max pooling 2D. And there is also for pre-processing image data generator. I will explain what all those layers and the image generator do. So the next thing is, since we want to train our data, to train our model, then we want to save the model. And then inside of our application, we want to load the model and work with it. So I made a mistake here. This should go into the train dataset, train file. So in order to get our data, head to the following website, go to kaggle.com. You could use some other dataset. I'm using the FER 2013 images, where we have exactly 958 files or images from an angry person, from a disgusted, fear, happy, neutral, sad, and surprise. So for example, if you open this, you will see there are a bunch of images, black and white images that represent people experiencing a certain facial expression. So you could use something else, but I'm just going to download this one. After it has downloaded, we can extract the files and move it to our desired directory. I have moved the data to the data folder here. Under test, you can see there are our images, and you can see there is also the images under train. And I have also created a folder examples where I will upload recordings of myself to test the application. You of course can use this live on your webcam, or you can use a recording. I will explain you how you can do that. Okay, the next step is to actually work with the data. So I have created a train directory and a validate directory, so which is under data train and data test. So now we need to create an image data generator, which is going to generate a data set from the image files in our directory on a scale from 1 to 255, since we define our images in pixels, which is nothing else than just an array consisting of a value between 1 and 255. We are creating the same thing for our training and validation data. And then we are going to create our generator from the data we have just imported here. There's a few things we can specify here. A target size of our data, which is going to be 48 by 48 pixels. Then we can specify a batch size. The batch size is a term used in machine learning and refers to the number of training examples utilized in one iteration. Then we can specify the color mode. We are going to use grayscaling. So this is for gray scaled images and black and white images. And the class mode, which is categorical, since we have categories of angry, disgusted, fearful, and so on expressions. Now let us create our model and prepare it for our training. So I'm going to paste in a bunch of code here. which looks pretty strange here, but I'm going to explain it line by line what everything here means. So here we are initializing a new variable, and we are initializing a sequential model. So by using Keras, we have two options here. We can use a sequential and functional one. The sequential API allows you to create models layer by layer, which is the preferred way for most problems. But it is limited in that it does not allow you to create models that share layers or have multiple inputs or outputs. Alternatively, the functional API allows you to create models that have a lot more flexibility, as you can easily define models where layers connect to more than just the previous and next layer. So this means you can connect layers to literally any other layer, which is quite powerful, as you can imagine. But as a result, it is much more complex and a lot more things become possible. But for our case here, this will be too complex and unnecessary. So we are going to initialize a sequential model here. Now we come to the interesting part. We can add layers here by just specifying add. So we have added a lot of layers here. So remember, this is the thing that we have shown in the graph earlier. We have said that we have certain layers here. And if you have more than 2 layers, then it's a deep neural network. And those are exactly the layers that we are specifying here. And since we are creating a convolutional neural network, which we have mentioned earlier in this video, but let us explain one more time what this exactly is. It is a special type of neural network that is very effectively used for image recognition and classification. They are highly proficient in areas like identification of objects, faces, traffic signs. They are used in self-driving cars, robots, and so on. A convolution is the simple application of a filter to an input that results in an activation. So there is some certain input and there are certain thresholds, and when that input meets those thresholds, then there is an activation, which you can see here, for example. Repeated application of the same filter to an input results in a map of activations, which is also called a feature map. So if there is a certain type of input that goes in and that input repeats itself in a certain way, then we can already see that there is a map forming, a feature map also called. That's indicating the locations and strengths of a detected feature in an input. For example, in our case, that's going to be a bunch of images. So as you can see, the strength of this is that we can access that we can have a lot of features defining certain categories and types, which we can then use to train our model on, instead of having all those features typed in a manual approach. So let us explain what each of those layers does here. So the first layer is a 2D convolutional layer. So this layer creates a convolutional kernel that is convolved with the layer input to produce a tensor of outputs. So we provide the input shape here, which is 32. We specify the height and width of the convolutional network, which is 3 by 3, and the input sphere represents our pictures, which are 48 by 48, and they are also grayscaled images. And here we specify our activation. This RELY stands for rectifier, which is an activation function used in neural networks. So it is one of the most common used activation functions. There is also the math behind it, which you can look up, but this is quite complex and we are not going really to cover it any deeper. But for your knowledge, in most cases you're going to use Arial U, but you can of course see the math that stands behind it. So here we are again creating a convolutional 2D network. So the max pooling 2D is going to downsample our data. You can always refer to the documentation here under keras.io. But what this means is downsampling means training on a disproportionately low subset of the class examples. So the reversed one would be upweighting, which would mean adding an example weight to the downsampled class equal to the factor by which you downsample it. So we are downsampling it to include less data, a smaller subset of the data. Then we are using dropout. The dropout layer randomly sets input units to 0 with the frequency rate at each step during the training time, which helps to prevent overfitting. So overfitting means that a model that has learned the noise instead of the signal that is considered to be the required signal for learning. So you always get certain signals and you always get certain noise. You don't need the noise. Overfitting means that you take the noise, so to say, too seriously and train the model more on the noise than the actual data that you need. So that's what the dropout layer is for, to reduce overfitting. Then we have again the same layers here. Again, dropout. Then we have a flatten layer, which we need to flatten it before we turn all those neurons that we have, that we are going to have here, into those 7 neurons here. So I'm going to explain this in a second, but let us first explain the dense layer. The dense layer is a hidden layer which is going to contain 1024 neurons. So this is the number of neurons or units that this hidden layer is going to contain. And then we again have a hidden layer here, which only contains 7. So this layer has to contain the exact number of possibilities that we can have. Since in our data here, we have angry, disgust, fear, happy, neutral, sad, and surprise, which are 7 categories that we can have. So we specify, we have to convert all those 1024 units into those 7 here. So this is what we have drawn here. So let's imagine here we have a lot more neurons going in here, but we have only 3 categories that we need to output, and we need to convert all those neurons into 3 here. So as you can see, this can become quite complex. The programming side of it is not that complex. You have to just specify a few types like the activation, your pool sizes, and so on. But the complex part is actually coming up with what layers where to use. For example, this is a standard approach that is well documented and used in a lot of papers to train for exactly this purpose here. So I didn't come up with this on the top of my head, but rather used a paper and some forums to reference on people's results. So people claim that they got really nice results by creating a layer like that. So this is going to be the major part of machine learning as it is. So you are going to be able to see a lot of, you're going to be able to learn all those things quite easily and learn what functions stand for what. But the problem of it, the complexity of it, goes into designing those networks for certain purposes that are not documented yet. Now let us actually compile our model, train and save the model. So what we are going to do here is compile our model. Then we are going to fit it to start training it, and then we are going to save the weights. So this is our model. We are going to train it, calculate the weights and save it as here. So in order to compile, we have to specify certain things here. So we can specify a loss, which is the degree of error. The models try to minimize loss, but they don't try to maximize accuracy. So we are using the optimizer atom here, which is the most complex part to say. It is quite mathematical and gets quite complex under the hood. But it is a very standard optimizer that is used for creating those models. So the categorical cross entropy is also the most common one, which is just the type, the metric, how we are specifying our losses. Since we need to specify the metric that we want to track, and we want to track our accuracy, we are going to specify accuracy as our metric. Okay, now it's time to train our model. So we can specify certain things here, like the train generator, the validation generator that we have specified earlier, the epochs or number of iterations we want to do it, and steps per epoch. Since our batch size is 64, we are going to divide it by 64, and we are using this divider here to round up to the next whole number. And then after this is finished, we can just save our weights here, and we are going to save it in the source folder. So now, in order to run this, open Anaconda or your terminal here. We're going to navigate to source, and now we can start training it. In order to do that, just I need to save this before, just type in python train.py.